Well, hello everyone, and welcome to my talk. I represent University of Freiburg, Germany, and I hope you're not really fatigued, as my specimens were. So let's get to the point. This is just the presentation plan, some motivation, material properties, experimental setup, processing algorithm that we have developed, and the results. You know, as the material science move forward, so the industry and we need materials which should be better, which should have higher fatigue properties, fatigue limits. And to do this, we need to test them. So one of the most advanced methods of testing materials in very high cycle area is ultrasonic fatigue testing. I think you've probably have heard about this already. We have several talks about this topic. So it's just the specimen is resonating at 220 kilohertz, so you could achieve like billion of cycles in a week or so. It's really an effective and rapid method. However, we're not really able to see the development of fatigue crack and the damage accumulation during the fatigue crack initiation. That's why most of people uses some additional monitoring methods, and the basis is the resonance frequency and the nonlinear parameter, which is just it's calculated from the first resonance mode and the second one. And as you can see on this graph, so basically near the fatigue failure, our frequency drops down drastically, and our nonlinear parameter goes in the other way around. It goes up. So the question is, what happens here? So to answer this question, these two methods, they do not provide a clear picture of this. However, that's why another methods are implemented. And our approach, we have thought, okay, let's take acoustic emission. This is the most sensitive method if we want to see what's happening in the material, because anything which is rapid and local in the material, it produces acoustic wave. Either it's a crack or a dislocation movement or phase transformation. We could hear it actually. But the problem is, as you saw already, we have a resonance frequency at 20 kilohertz, the second peak 40, 60, and so on up to almost infinity. How to filter this out? This is the question. So far, no one have managed to deal with this. Just a few words about the material. We have taken the aluminum silicon copper alloy. We have this kind of phase where we have aluminum silicon eutectic matrix, which is quite ductile, and we have this alpha intermetallic particles, which are quite brittle, and they serve as a good crack initiation spot. And the geometry, the specimen is designed to have an exact frequency of 19.5 kilohertz. This is the experimental setup, just a photographic image. You could see the 3 computers actually were used. So this is the vibrating horn. This is the close-up look. We use air cooling as all the other researchers, and this is our specimen, which is resonating and undergoing fatigue testing. This is just a scheme of this. We use infrared camera to monitor the temperature, so the specimen would remain around 20 degrees. And we use the acoustic emission sensor, a broadband 2 megahertz sample rate, and a filter. So we record the acoustic emission in a threshold-less mode, so we record everything. It's just a stream, and it looks like this. If we would do a Fourier transformation, short time Fourier transformation, we would see that our power spectrum looks really like a brush for your hair. You see, these peaks comes from the resonance frequency, 20, 40, 60, and so on. So how could we filter this out? Of course, not using just a physical-based filter, broadband. So the algorithm was designed to use the MATLAB environment. We just used peak detection based on this, and we filter this, all of this, with a power spectrum density. From the power spectrum density, we filter out all the peaks, and in the end, we obtain a smooth power spectrum density. Then, if you would see this filtered spectrogram, if you would just sum up, this is the time axis. If you would sum up on every time moment all the power, you would have the filtered power then. And then you can just apply a simple threshold method. And you will obtain events power, and then if you sum up, you would obtain the cumulative power of acoustic emission events. Now, let's get straight to the results. First, I would like to show you the results of a surface crack. So again, the resonance frequency drops down. This is the nonlinear parameter, it goes up. Something is happening with acoustic emission. It's not quite clear what is happening. Here, everything is smooth. We don't see any particular zones or knees on our curves. However, if we would look on the acoustic emission events power distribution, it have distinct steps, and the amount of steps coincides with the zones of fatigue fracture, which you could see. This is the optical image, and this was the spot where the crack initiated. And you could see clearly with the color, which represents the roughness of the surface, and this represents the different modes of fatigue crack propagation. So we have a good correlation here. Let's move forward. This is the internal crack propagation. You see here the photo, a large cluster of intermetallic phase has initiated an internal crack. It was developing inside the material. And what is interesting, the moment at which this penny-shaped crack reached the surface, we have really a high burst of acoustic emission activity. So we could actually hear this. And again, the amount of zones somehow coincides with the amount of zones in the fracture. Before I go to the next step, maybe after this. So this is the reference state. After the fatigue testing is done, we need to break the specimen manually by cooling down in liquid nitrogen, and then we break it. So with the reference state, we knew that there should be no crack, so we stopped the experiment preliminary. We broke it, and we could see no fatigue crack at all. And as you see, again, acoustic emission results correlate perfectly with what is going on. So we have no activity. However, when we use a standard linear parameter, a nonlinear parameter, it goes down, so something is happening. But again, it doesn't show us the clear picture. However, the acoustic emission method that we have implemented clearly shows a good correlation with fatigue, ultrasonic fatigue testing. So, yeah, just to summarize quickly, we have developed a new method of implementing acoustic emission for ultrasonic fatigue testing. It really works. It has a good correlation. And in the end, I would like to thank German Research Foundation for financial support. And I would like to thank you for your attention. Thank you.